have to point exactly. Must be like this, right? No, pointing here.
Yeah. Then if I need to, a little bit.
What?
I perceive a laser.
No, you have to go
little-
perpendicular. Go perpendicular.
Okay. Wow.
Or you can
It's really 90 degrees. Plus minus 10 is well, okay, never mind. I can always point on this.
Always like to slide.
Yes, yes. This one works.
Someone online available or not?
No.
Let's start.
If you lock the door.
No.
I go.
So, hello, welcome everyone. We have Eugenia talking about n equals to supersymmetry. So, please, follow yours.
Welcome. Thanks a lot. I'm very glad I've accepted Basil's invitation. We met in String 2 weeks ago. It was very nice. And I'm very glad to present some work we've done in collaboration with Ondra Hulik, whom you know as well. Yeah, so it's going to be about n equal to supersymmetry on the word line, BV and pictures, which I will explain because
what does the picture
it's going to be
symbolize? The one in, no, that's not the picture. The
okay.
one in the first page. This one.
So this is the logo of Comenius University.
So there's an atom. That
Yes.
is a photon.
I think
Satellite and integrals.
What's a satellite?
Sputnik. Sputnik, of course.
Oh, wow, yeah.
Yeah.
Thanks for explaining. I didn't know about the Sputnik. Okay, cool. Right, so some motivation could be that it's convenient to treat particles more or less as strings, only one dimension less. So we consider some particle sigma model. So from an interval to a target space. And we would like to understand, in fact, to use this as a toy model to understand better aspects of superstring theory. For example, which backgrounds are fixed and what could be an action functional for the second quantized string, because in string theory we know how to compute the scattering amplitude, but we don't have, we have only just a few well-defined action functionals. For example, Witten's cubic string field theory. Right, so as I said, that this is based on an article that you can find on the archive. It's still not in the final form, unfortunately. We are working on that. It's with Pietro Grassi, Ondra Hulik, and Ivo Sachs. I want also to mention that I have been doing some discussion with my master students, Marian Lukac and Lubos Shavas as well. So that's the outline of the talk. First, I will explain what the model is, and then we will move on to BRST cohomology, how the partition function will look like, which states we will find there, and then classical BV action and interactions is the part that regards the target space field theory. So let's get started. This is the model itself. So it will be called also spinning particle because there is a supersymmetry on the word line, and it's classically known as spinning particle. So for n equal to, you know very well that you just need to superspace formulation, right? You need the fields to expand them in power series of Grassmann odd variables theta and theta bar. E is an Einbein, and I wrote it in this way because I think it's convenient. Although in general, the action functional for n equal to, I think it's usually presented as a generalization of an n equal 1 action function and so on. That could be, I think this works, but it's just my own calculation. So, well, some differential calculus, we need the derivative with respect to the parameter tau, then we need the super derivatives, and we form an action functional by with this object. So it's an integral over the line, it's a line integral, then there is an integration over the Berenzin integral. Here we place our Einbein, and we have a kinetic term for the superfield phi. Then if you proceed with the calculation, you take the Berenzin integral, and actually you already switched to first order formalism, so you replace x dot and other stuff with p, as you know. Then
Is there a geometric way to see this capital E? Is it some kind of expansion?
yes, as well, yes, in power series of theta.
Yeah.
Usually it's
Yeah, so
1 over e. In fact, I decided just to recollect everything in
so it's
this
1
form.
over E in a shifted point.
1 over e with a different e.
Yeah.
Then you go on and you do the power series expansion. So this is our classical action of a n equal to spinning particle.
So,
Yes.
you skip any auxiliary fields in
Yes,
the second
exactly.
case.
Yes, sorry. Of course, you're right that there will be also, it's allowed to have a term that depends on theta and theta bar as well, but they are just a Lagrange multiplier and they can break now. They don't have any dynamics. Good, so yeah, sorry about that. So there is a kinetic term, there is also some constraints here. This will fix the mass to be 0, and the other implied that, well, psi bar, which can be interpreted as gamma matrices, are orthogonal to P.
So you say it works, so I just need to
Sure. Sorry.
understand it in its calculation. So you say taking the Berezin integral, that's fine,
Yes.
and switching to first order formalism. So you take what you get after doing the
Yes.
integration, and then you from that you define the momenta,
Yes. The
and
moment.
then you write the action as p x dot minus
Minus the Lagrange.
so,
Yes.
In the
Minus
first
the
order formalism, you also solve for the convection or just define the momentum with auxiliary convection?
which connection?
But if it is first order, it means that convection is dependent, right? Independent.
this is a bit different. You canonical formalism. You're thinking first order, second order in gravitational
Yeah.
language, but this is not gravitational language. This is like you can write Lagrangian using
Hamiltonian
language. Hamiltonian language, right? But the first term shouldn't there be an x dot in the first is there like px dot, or is it really px?
Wait. You are no. Wait, it's correct. No. You're right. Yes, it's excellent. Sorry. Good catch. Yes, of course. Okay. Right. So indeed, this is all. But our starting point, we can see that it leaves a Hamiltonian system defined with a graded Poisson algebra on the functions with these Poisson brackets. So the first brackets involve the psi and psi bar, which has gamma matrices, and then there is a Poisson bracket between x and p, of course, canonical one. Besides the free for some brackets, we also have a Hamiltonian action on the symplectic structure. It's given by G1,2 algebra. So there is one even generator and two odd generators. It doesn't really matter their expression that can be derived, induced from the super covariant derivatives here. And the important thing is if there is a super Lie algebra with a Hamiltonian action on our symplectic model, then there is a moment map, and the components of the moment map are exactly the constraints of p square and orthogonality between gamma matrices.
And the super Lie algebra, is that GL1/2? Or when you write G?
Yeah. I left the G in order to not make things more complicated, but it's super. Super translations or superdiffeomorphism on the line.
Okay.
And then, yeah, in this notation though, because it will act on the target space where XP and psi is. Okay, right. So instead of talking about the functions of the symplectic quotient, the way to deal with these constraints for me is BRST, which replaces in fact the function of a symplectic quotient by a cohomological problem. So it's a rephrasal of this problem in terms of BRST cohomology, right? So instead of trying to describe the function of this symplectic quotient due to the action of these superdiffeomorphisms, well, in a nutshell, you have to pick up the G-invariant functions on the inverse of a moment map evaluated at one regular point, could be 0, could be any other regular point, and then you construct your complex by building a causal resolution. So you have to make sure that there is cohomology on the 0 degree, 0 order. Everything else cannot have cohomology. And indeed, you even need a double complex, not just a one-line complex. And then the fundamental theorem of BRST says that the functions, the smooth function of the symplectic quotient are encoded in the 0 for the BRST cohomology of this double complex. So this is just in a nutshell to explain why it's important to switch to BRST when you have constraints rather than studying the symplectic quotient. So now I would like to make a bit of a comment, a disclaimer, because I will use BRST a lot, but in two different facets, in two different maybe settings. So first, maybe you're more familiar for sure with BRST transformations that act on the fields. So for example, in Yang-Mills, you can consider the field content given by the one connection, one form in U, that's mu. Then you need a ghost C, and you need also a trivial pair that we call B and C bar. C, B, and C bar are scalars. Then BRST transformation on the fields look like this, as you probably remember. So B and C bar are indeed a trivial pair because C is exact. Yeah. Q is an idempotent differential operator with some ghost number 1. So these are BRST transformations on the field. But in my work, okay, this will appear, and also we will focus also on BRST cohomology. At some point, we will switch between these two descriptions. BRST cohomology is exactly what I was trying to explain before. So there is a you have a Lie algebra with a Hamiltonian action on a manifold, a moment map, and BRST cohomology is the cohomology of the complex. This is what was before CP comma Q. So you need well, some px0 powers of the dual Lie algebra, of the coalgebra Q of the Lie algebra, tensor with functions on M, and the nilpotent operator is constructed with the components of a moment map and the structure constants of the Lie algebra, and it's guaranteed to be nilpotent because the structure constants satisfy a Lie algebra, so Jacobi identity for the Lie algebra and other conditions that follow from the moment map. So this is. So we will focus on this part first, and then on the BRST BV of a field theory that will come up in target space. Okay, so the BRST complex of n equal to worldline comes in this way. So this is the notation. So we need a graded symplectic structure on the exterior algebra of G star direct sum with G. We have Ghost and anti-Ghost. I already wanted to highlight that there is an extra symmetry in n equal to, it's U1 symmetry that rotates the supercharges Q and Q bar. Therefore, also the Ghost and the anti-Ghost will be charged with respect to the asymmetry, and the charges are shown in the opposite of a superscript underscore. Okay, C. Okay, so we have C gamma gamma bar, B beta bar, and beta. And we will consider this BRST complex as I explained before. I want to just point out that it's curly M because we have coordinates x, psi, psi bar, but nothing too fancy. And I just have written down Q, how Q will look like in our particular setting. So components of a moment map contracted with the Ghost, and then this is the part that depends on the structure constants. Now we should maybe address a bit of differential geometry on supermanifolds, because that's a big elephant in this room, I will say, because indeed.
Sorry, can you go back one slide? So Q has ghost number 1, capital Q ghost number 1. So gamma and little q bar, and so what do they have a ghost number? So you have gamma plus and minus as ghost number. So the q bars are shifted with 2 and 0 and something like that.
So this expression has ghost number 1, right? Because ghost, 2 ghost and 1 anti-ghost.
So the q bar and the q have ghost number 2 and 0 or something like that. Or let me see. So
with the I got lost. Are you asking about the ghost number or the R number?
The betas are anti-ghost. Q, gamma and gamma bar are both ghosts. So they both have ghost number 1.
Gamma and gamma bar have both ghost number 1,
or
yes.
What is the index?
What is there's some index?
No,
there.
So
this is not ghost number.
This index
is
the
the
U1
R
R
number.
number.
Okay, okay, good. But they still have ghost number plus 1.
Yeah.
Yes.
Okay, good. So the Q's have ghost number 0, little Q's.
Right.
Yes, yes.
Those are the super generators.
Okay, so the funny thing is that in super geometry, I've been told that you can construct more forms than in the usual classical geometry case. So, for example, if you suppose to have some manifold of even dimension m and odd dimension n with respective coordinates x and psi, Now, there can be different types of forms labeled by the picture number. In picture 0, there are superforms. So even for the odd coordinates, we can cook up a differential d of these odd coordinates and just declare this superform to be indeed a form. It fulfills it. A complex remains defined like this. You start from the constant functions, and then you act with by wedging with the axis or deep size. So this is picture 0, and it's called the superform. In maximal picture, instead, there are integral forms, so-called the integral form, because a superform cannot be integrated, indeed, because deep size are the differential of not the coordinate, therefore it's an even object, and there is no good notion of integration of this form. Therefore, we switch to integral form in order to have some integration, and integral form, rather than being constructed starting from constant function, you start from by contraction or by also derivative of a distribution of a Berenzinian sheaf, which is a section of a superdeterminant bundle. So they are these integral forms have maximal picture, and they are represented in this fashion. So you still have the axis for the even coordinate, and then you have it's distributional in the d of the odd coordinates. Now the complex can go arbitrarily low in form number, because derivatives on the Dirac distributions decrease the form number. Yeah, so that's it. So it's bounded from above, whereas the superform complex is bounded from below.
And the Q and the R again is ghost number and R.
No, they are just. Sorry, I could have chosen different letters. They are just some letters. There's also an interpolating case in between 0 and maximal picture number, and it's called the pseudoforms. So some of the odd coordinates will be represented as dx, the deep size, and the other will be represented with the Dirac delta. Now the complex is non-bounded, neither from above nor from below.
So you say that this gives you a way of integrating when you use the delta functions.
Also, yes.
So how should I see that? How should I think of it to see that it's no way of
Well, for example, you can, indeed construct the maximal picture also form that you need by wedging with pseudoforms or by wedging directly with the integral form. Whatever your starting object is, then you can take the wedge product with something else, and then that's a well-defined object.
and then you're happy because it's antisymmetric. That's
Yes.
you get the maximum.
Yes, you're happy. Yes.
So this is in a nutshell a way of constructing the Berezinian integral that instead of integrating we differentiating the effect.
Right. In a sense, or
In a
I mean, so the deep size are not grasping.
right, but it should give me. I mean, in the end, we integrate out the size, right?
That's the question.
So when we do the integral, does it depend on psi anymore?
no.
So it seems to be a trick how to encode the rules of the. I mean, this is a generalization, of course, especially the interpolating case. But I think it's like a shift, which is more natural. To for instance, you can code the standard BRST integral in this case.
Yeah, I will say so. Right, it's
So I think the standard BRST there will be that the Grassmann odd variables we would differentiate all of them. If we have any, then we differentiate this. So I'm wondering whether the delta function and size can be viewed more or less the same in the top form.
so eventually you want to go back to something that is indeed, as you are saying, doesn't matter. So you have some big psi 1 and big psi 2, but then you also have prime. This cannot work. This is one, right? So you want to try this one. Yeah, generally. No, sorry. I was. So you need to do some d of big psi 1 as well. And this will give you 0. If you do this, then everything is good. Yeah. I don't know, I'm probably making more confusing. It's also not really. Maybe this time works. Okay. But we have limited time for that. No, okay. Okay, so forget. Okay, so let's work with just the, suppose we need to take, we have just one, then of the Grassmann of the coordinate psi. The only object that we can integrate is this one, by definition of direct delta. Therefore, this would give us 0 instead.
What does the one? Does this a prime or this is a 1?
It's a derivative.
So
Yes,
there's
so
a
it's a prime. Yes.
is a plus.
So indeed, that you can think of this as maybe writing a
And
0 form. So picture 0 form, wedge maximal picture P form, which in this case is 1, because I decided.
oh, okay, so the first one is 0. The prime is 0. Are you saying that? The
So I'm saying no matter what the form degree is, this is the picture number. So it says it's in picture 0. Each side is a picture 0 form. Actually, maybe we can need to say it's a 1 form in picture 0. Let's say it's 1 form. And then the good notion of integration is with in this example would be P equal to 1. And then I don't want to counter the form number because it's a bit more complicated. So then this is the good benzene and
okay, and how do we get something which is non-zero? How do we get something which is non-zero? in the first example.
Or, well, you can always try to cook up something with.
I think for
D minus
simplicity,
K.
before we get to the omega, can you go back to your D, just your example with the D size?
So which one did you want to?
I would like to see the integral with D size rather than omega, because I don't understand what omega exactly is.
Right, that was, okay, so this was the most easy example, so you say,
And
say
so
M
the
is-
non-zero means
so I have a big size and okay, there is no interpolating case here of pseudoforms. Either I write down superforms or integral forms. Anything else will vanish.
So is it deep side or deep side?
I always get confused, probably.
but because D side,
You're
I
right,
guess it's
it's D of deep side, yes, yes. It's easier if you do this trick, which you label this as some other, so then you write it as dt of delta. Yes, okay, perfect, sorry.
And the indices on omega, the first index is the form degree, and the second index is the picture,
Yes.
and you need the picture to be maximal to have a non-zero.
But you can, yeah, could come up from even
Right.
pseudoforms as
Yeah.
long as the maximum picture is achieved. Right, so there are now some important operators that I want to mention. Some are called the picture changing operators, which are cocycles, therefore they can function as chain maps. They send cohomologies into cohomology, and then there are Hodge star operators. There's it's possible to define a Hodge star operator that takes, it's an isomorphism and takes, I should have written it's an isomorphism, it takes a Q form in picture K to some other form degree in picture P, being the maximal picture minus K.
So what gives you the F?
And that's difficult to write down in one formula.
Is it fixed or can you choose?
You can choose.
You can choose. But then doesn't it mean that like there are
Yeah, well,
different Hodge star operators? Or
that can be different.
they can- And for each
As long as you have an isomorphism, I just need to map isomorphically the spaces.
so sorry, I still don't get what the picture is. What is the picture?
the picture is like somehow the thing that you have to put enough delta functions somehow resolve.
Right, is this like the anomaly? I mean, we always had to prepare to get a non-zero integral.
Something like that, but it's there's something more to it than just like Grassmann integration. It's similar, but it's not quite the same.
Okay, so where does the so what's the simplest p equal 1? Okay, the simplest non-zero picture. What? So p equals 0. I assume that's just Grassmann integration or what? No. Okay, so
No, you don't have integration. P equals 0. Either saying P maximal P equal to 0.
okay, so
You don't even have the of the Grassmann.
okay, so I don't know what is maximum p, and what is minimal p, or what is
Maybe in when you have one coordinate,
yeah.
either you construct a d of this coordinate or delta of d. So this is in picture 0 and this is in maximal picture equal to 1 in this case. Suppose you have
Oh, so the picture is something with delta functions?
Yes, so picture is maximal when all the,
So picture is
the-
a number of delta functions?
picture is maximal when all the coordinates are represented as delta of t.
And if there is any number of odd, would we then
So
call it
let's say
picture
you
n?
have psi 1 and psi 2.
Yeah.
This is a pseudo form in picture 1.
Okay.
Like this, instead it's the integral form. Okay, actually I have other examples. So this is the pseudo, and then the super form is.
So the maximal is the one that you can integrate.
Yes.
So, and the first is omega 2, 0. The second one is omega 1, 1. The third one is omega 0, 2.
Yes. In this case, it's simple, but then we could then start taking as many derivatives as we want, right? And then the form degree changes.
Right.
Oh, so there's also derivative of the delta function?
You can do it, yes.
And does that change the
Because
picture?
the delta x equals the benzene and the lattice.
And does this picture change when we put derivatives on the delta function?
Yes.
Yes.
So they shifted accordingly.
And they get less, the picture decreases with each derivative.
Yes. Because wait.
So I can
So
put a delta function, a derivative of delta function, then it will still be at the picture 0.
There will still be a picture. Yes. So you can put a derivative.
It's that if you can, if I take a derivative of a single delta function, then it's picture 0.
No, it's whatever picture it is. Depends if you. So if you. So something like this. By using the distributional properties of the delta can be written again as like this. So even if this looks like maybe a pseudo form,
Okay.
then it's effectively an integral form. So then you can do this kind of things. So yeah, also maybe a criticism I've heard of picture changing operators is that
So if there's no
kind of a coordinates, right?
So if there's no derivatives, then on delta function, then it's just a number of delta functions. That's the picture.
Yes. Right. So I've tried to illustrate with an example what an odd star operator could be. So if you suppose you are in maximal picture number 1 and you pick a 1 superform. So you want to know star of deep psi. Well, let's call deep psi t. Let's relabel into t. Let's take a Fourier transform of it. We notice, okay, that comes with an extra factor of k, so it's a derivative with respect to t. So we notice it's the integral representation of a delta, and therefore it's a derivative of the direct delta of t. But let's go back and recall it. The t is deep psi, so it's
very tricky. Okay.
it's very tricky. Yes.
Yeah, you have to get used to this. Okay, so you say the Hodge to outline, is that something common that Hodge dual of something you get by Fourier
Yes.
transforming? That's something.
In this setting, I learned from Pietro Grassi because so, right. However, another point to be stressed is that we want to do this over a Hilbert space. So we will set a ground state and declare some of the ghost and anti-ghost to be annihilators. So we are going to a Lagrangian subspace in the symplectic setting. And indeed, yeah. So all the barred quantities will be annihilator. B is also an annihilator, and P, of course, as we are used to. This slides just want to show how superform, pseudoform, and integral form will look like in our setting of n equal to spinning particles. So superforms, we call them just with C, gamma, and beta. Because of relabeling D of not the coordinate as just one parameter, gamma or beta. And also C is odd, so there can only be either one C or no C at all. But gamma and beta are even, so they are. I can construct polynomials in gamma and beta, and pseudoforms would be of this type. Integral form will be maximal in yes, in the gamma and the beta. And there can also be derivatives. I hope this was set correctly. Okay, so now we set everything up. I explained a bit about the forms in supergeometry. I wanted now to switch to the partition function that comes out from the model of a spinning particle. But the focus will be on the Hilbert Poincare series because it's we found it as a convenient trick, and I kind of liked it, so I want to try to explain what this is. The Hilbert Poincare series is a multivariable series defined for some vector space that is filtered or graded into some other finite dimensional vector subspaces. And it corresponds to this sum in some different variables over the dimension of vector spaces with different fugacities n, p, or k. It's also the trace over V of t to the n seen as some operator acting on the vector space. Comments on this Hilbert Poincare series are the following. So if you suppose that there is some differential D that can increase the degree of one of the degrees between which the vector space is divided, then the Hilbert series in T and but with S that corresponds to this degree K, this value K, set to be -1, then it's some filtered sum over the dimension of the cohomology groups. And this happens because, well, it's a one-line explanation. So you can write VK as the closed elements with respect to D, indirect sum with the non-closed. Then you notice, okay, if I quotient with the exact ones, I get the cohomology exact in degree K. But then you can also notice D in the over the non-closed is an isomorphism with its image, so it maps to the exact one in degree K+1. So that's how each dk can be decomposed. But if you sum over all of them in K, then you have sum over the dimension of all of that. That means that you have an alternating sum, a -1 there. So the co-boundary will drop out of this. Hopefully it's convincing, but so the series, it's just a redefined, it's a series that filters the dimension of the cohomology, and also you can cook up also the Euler characteristic if you just set the T and R equal to 1. So now you're wondering why we are doing this. Well, it's because we have BRST, so the point would be to use indeed the BRST operator to find the expressions of this type once you set up the series itself. So indeed, the Gauss number, it's the number that we have. It's the cohomological one. N equals 0 will correspond, oh sorry, I changed the, no, n here. So we are in, or let's say t equal 1 or n equals 0 corresponds to the picture. So let's work at picture 0 with the superforms. S is the Gauss number. Also, now it comes to hand the fact that there is the U1 R charge, the U1 symmetry. So the extra parameter, the extra variable that we take into account is precisely a variable that serves for the R charge. It's related to the R charge. So the point now is this partition function can be constructed as a Hilbert-Poincare series by just noticing that there is a scaling behavior of the elements of our Hilbert space. So the Gauss, the anti-Gauss beta scales as R over S because S inverse because it's an anti-Gauss. So it has Gauss number -1. And R is 1 because that's the R charge. So it's R is to the power of 1. Gamma is a Gauss and has R charge equal to 1, so it will scale as Rs. Psi is a normal coordinate, there's no Gauss nor anti-Gauss, so no S will appear, S to the power of 0, but it has some R charge because it's part of the supercharge itself, as you remember. And C is purely a Gauss that doesn't have any R charge, so that's how they're scaling. Oh, sorry, I went back. And now it's a matter of counting, maybe with a negative degree, a negative sign if these objects are fermionic. So maybe it's more of a twisted partition function or an index eventually. So you count the number of psi's, the number of C, gamma, and beta in your that will make up your full Hilbert space. And the Poincare Hilbert series will look like this. So 1 plus R to the power of D, so the dimension for the of a target manifold M, which is not set to be 4, can be any dimension. 1 plus S from the C, right? It's either no C or 1 C.
Or it's because of the number of coordinates, essentially.
Yes. And then this from the beta and the gamma because I recollected the geometric series. And now you can expand in collect a 1 plus S in front, and you expand and you get the following that, of course, R charge is 0, there is 1 degree of freedom, it's a scalar freedom. R charge 1, you have D, this is from a Gauss, and this comes also from a Gauss, so eventually it's subtracted, so you have D minus 2 degrees of freedom. So this can be a propagating vector field, for example, a photon. Vector freedom 1. And then in R charge 2, you have 2 forms minus some, some degrees of freedom are subtracted and then put back into the game. If you do this for a 4-dimension, probably it makes sense, and it does make sense, and you find it again. So this will be 6 minus 8 plus 2, I think. So 0 because, is that right? Because in 4D, a 2 form cannot be propagating. Is that right? I think so, right? 6 minus 8 plus, no, or sorry, there is a plus 1 eventually, plus 3, so there is just 1 degree. Things like this.
Right, and you had a third fugacity T, which you put,
Right.
you eventually want to put to -1 or something like that, right?
Yes.
And
it's
that's
not
how you
present.
change the sign on the ghost.
No,
No?
the sign is changed differently.
Ah,
Uh,
well, so
yeah,
the S is -1.
yes. Or it's flipped from, yeah, from S to -S.
Yeah, I think, well, there should be 1 degree.
Yeah, okay, so 4 times 3 divided by 2 minus 4 minus 4 plus 1 plus 1 plus 1.
Right, so that makes
1.
sense.
Okay, so as I said, if you were pointing out T was set to be 1 or n equal to 0 because we wanted to work first in picture 0, so with the superform, but then the discussion can be extended to the other cases, and then we find out that the same result holds for picture 2, because it happens that with some Hodge star operator that we chose, Q is the Hodge star operator is a chain map with our BRST operator. So the BRST cohomology in the superform sector, whatever the dimension of the cohomology groups are, well, the same will be true in picture 2. And in picture 1, instead, we can find the same partition function for the same result, the same dimension of the cohomology group, because of the picture changing operators, which is possible to find because they are quasi-isomorphism. They map cohomology into cohomology. But this is the case only in the square, the box, where all the chain complexes can be mapped into each other, right? So, for example, the integral forms were extending arbitrarily to minus infinity for the form degree, and well, there is no chance to find a star or a picture changing operator that takes us to the superform sector. So indeed, it happens that at r charge less than 0, there are no dynamical states, so there are topological sectors. And here there is an explanation, and it's based on the fact that, well, you can construct your own module starting with these operators, psi derivative with gamma, beta, and derivative with gamma. And it turns out that the partition function will look like this, and doesn't depend on R, apart from here, but depends only on the ghost, and therefore there is nothing dynamical in there. So it's just a topological states. I think it's probably already known, and in fact, there is, for example, a Chern-Simon sector in Yamn's theory, right? So nothing too surprising. Okay, also I wanted to point out a detail, and the fact is here we have this type of degrees of freedom, but because we kind of, yeah, we would have maybe 2 copies appearing with different sign because of 1 plus s. And this is due to the fact that we are actually talking about a BV multiplet essentially. So there are the degrees of freedom for the fields, and then there is a second copy corresponding to the degrees of freedom for the antifields. That's what is happening in the background. So that's the observation that ends this section. It's an isomorphic copy. So we find this as well. Right. So since we have two copies, it means that indeed we are dealing with BV secretly, at least the free BV theory in target space. Definition of classical free BV theory. I'm following William and Costello. It's a cochain complex. There is a differential and a non-degenerate and antisymmetric pairing that can correspond to the BV symplectic form eventually. And this pairing is a cochain. In fact, as an example, for Yang-Mills theory, the classical BV theory consists of this complex. So there are 0, 1, 3, and 4 forms. And these are the Ghost number on top, right? So C is a Ghost for A star is the antifield for A, and C star is the anti-Ghost. The pairing is hooked up from this integral over n of a trace of alpha wedge beta with a sign that it's not the form degree, but maybe there's something else now I don't recall from the top of my head, and it just corresponds to this. This is the symplectic. I mean, it's the pairing, and you can construct the symplectic form from.
So
from
if you truly mean BV, then I think you don't need anti-ghost, but you need antifield for the ghost.
Yes. Okay, sure. But to be precise, you're correct. Antifield for the guess. Right. So now the statement is indeed BRST of n equal to spinning particle is already the free classical BV Yang-Mills. So you just have to consider as we've done so far. So this part of the cochain complex in R charge 1, and where you remember that we also did this over a Hilbert space, we were already quantizing, so we had half of the coordinates dropping out being set to 0. Okay, Q is the Q for BRST, and star is the Hodge star operator that I never written down explicitly. I've just shown you how it works in a simple example. So indeed, why is this the case? Because a generic vector in V1 has this expression. This has R charge 1, and it's constructed only from psi, beta, gamma, and C. So you notice already the labeling is convenient because it shows that there is a ghost, there are one form field, and there are respective antifields, but there is also an auxiliary scalar. This is not the most straightforward version of Yang-Mills, it's the version of Yang-Mills where there is an auxiliary field, auxiliary scalar. Indeed, okay, so you can also recombine the Gauss numbers for the C gamma beta, the elements that live here, with a Gauss number that you want to have on the target space field, so that this object, the whole object, has homogeneous Gauss degree 0. So since beta has Gauss number -1, C should have a Gauss number 1, A nu has 0 Gauss number. Phi is also auxiliary to A nu because C and beta together have Gauss number 0, +1, -1, and so on. And now upon some real definition, so you say, okay, cohomological degree would be minus my Gauss number, well, we can write down this complex again. Q now is not the Q BRST, but it's Q that acts on the fields. And yeah. So the point is only compared to the one for Young-Mills that has it's this the Young-Mills complex on form degree 3 and 4. Now for our correspondence, actually it turns out that we have form degree 1 and 2 more naturally. No, sorry, 1 and 0, sorry. Yeah, 1 and sorry, I said some 5 star has already form degree 0. So in any case, there is not a good match, but 5 was not appearing in the other definition. A star and C do not have the same form degree. And this is anyway fine because the BV pairing that we can write down thanks to the Hodge star operator is anyway here and has the right properties. It's defined as starting from the Hodge star, right? So it's half, because otherwise we will have a factor of 2 of integral over n in Berezinian integral of a trace of star of alpha and then product with wedge product with beta. So it doesn't really matter in this correspondence that A star and C star don't have the right form degree as before. However, this would give us some troubles when we were looking for the interaction, because so far we just shown, okay, BRST for the n equal to particle at r charge equal 1 as a photon, it's could, or a gluon, it's Young-Mills theory, free Young-Mills theory. Would be cool if we can also write down the interactions, but the standard way to write them down is by homotopy algebra. So very quickly, it's the algebra where the defining property, Jacobi identity in this case, is violated by extra brackets. However, there is some regularity condition on top of this proliferation of brackets, and an example of a homotopy algebra is this one for a Young-Mills connection 1 form. You can write the 3 the term with 3a in Young-Mills as a mu2 like this, and the quartic term in Young-Mills as a combined with a mu3 like this. So it's eventually stops here, and it's called the L3 algebra. It's well posed. So the interacting BV theory for Young-Mills could be just recast in this way. List of so this is now classical but interacting with a mu1 twiddle because here I presented only the classical part of the fields, but we can write multi-products also with antifields for the ghost and so on. Mu twiddle 1 is the differential. Yeah, so the action will look like would be some. You sum over all the multi-products that you have, and you integrate with some factor, and you integrate the trace of the BV pairing between some psi with a mu I of other psi's. And it satisfies the classical master equation because of the homotopy algebra property, the fact that the mu I have some relations between each other. Okay, so this is in general how to write down the classical interacting BV theory for Young-Mills, very roughly. However, when you want to extend this interpretation to the BRST cohomology of n equal to spinning particle, then we haven't been able to construct the multi-products on the Hilbert space, on some tensor product of the Hilbert space. If we assume that there are multi-products, then it's easy to find some L infinity morphisms between these multi-products and the multi-products in the target space where the Young-Mills theory is already. However, we would like to have an independent proof of existence. I mean, we would like to define them a priori rather than assuming that they exist. Therefore, a partial solution, let's say, but it works, it's by the formation of a nilpotent BRST operator. We decided by Ivo's idea to turn the nilpotent operator into a field-dependent one. So it picks the fields in the target space, which are the Young-Mills, BD Young-Mills fields, and then becomes some operator over the Hilbert space, which I call the V1. The expression is as follows. It's not important to memorize it, but you know, it's not totally arbitrary. It's been constructed by noticing, okay, the Gauss number of 5 star must be -1 because it's the antifield to a normal field. So it should come, yes, with 2 Gauss in front. Because Q is constrained to be a Gauss number 1 homological operator. And pi is the covariant derivative, and phi twiddle is a redefinition of phi with the commutative between P, the momentum, and B, which is another, it's just, yes, it's another one form field, and G mu nu is a 2 times. Right. So what happens is that when you distinguish Q into Q naught and Q1 according to the dependence, if it's not dependent on one of the BV fields, or if it is linearly independent of one of the BV fields.
And by BV fields, you mean the antifields, or do you need to do
all of them. So Q1 can also be
okay, or the full BV
multiplet, yes. So our proposal looks as follows. So we use this Hodge star operator again, and plus Q naught on this first term, and Q1 that acts on the beta anti-Gauss, sorry. And then a second term with a triplet of Q1. The point is that this is based on an operator state correspondence. If you can notice that the linear part of the Q deformed BRST operator acting on beta, on the anti-Gauss beta, gives us precisely 4, which is this, the generic vector in V1 in the Hilbert space. And then, okay, so this is to explain that the quadratic part, which is the first term, is invariant under BRST transformation, the regular BRST by Q naught. Then you can define some 2 product M2 in this fashion, and you can show that M1, this one here, that implements the BRST transformation, is compatible with this M2, and M2 is actually associative. That's it. It's not, there is no M3 here. And that's all, actually this BV theory has the BRST BV symmetry proper of Young's.
So in 6, can I think of the last term as the interaction term?
Yes. All the interaction is here indeed.
In one.
Even the quartic term of Young's comes from here. Right, and we've shown that also the equation of motion are retrieved. You can go through this calculations and we'll notice that they boils down to show that, okay, the equation of motion comes down to this commutator of Q, deformed Q with itself acting on beta equal to 0. And these are the BV Young's equation, but if you fix the auxiliary one form of B mu to be A mu itself and G mu to be -2, the commutator of a covariant momenta, pi mu and pi mu. That depends, it's P plus A in our notation. And there are no other solutions continuously connected to BV Young's. So this is the only choice you can make. So in conclusion, thanks for your attention already, because I've seen we're quite over time. So in the same way as open superstring theory describes a gauge theory in target space, also here the n=2 spinning particle consists of gauge forms. The one form satisfies Maxwell theories or free Young-Mills, free Young-Mills theory. Higher forms can satisfy a higher version of electromagnetism. However, of course, pictures bigger than 0 and negative arc charge have topological sectors. For the interactions, there is no, we weren't able to recast everything in the form of an L-infinity algebra on the worldline, but we went for an alternative approach by deformation of a Q BRST operator, and it worked. In the future, we are applying the same strategy in consideration to n=4 that should describe instead the gravity multiplet. Actually, NS sector of supergravity or bosonic supergravity at this point. We want to understand if there are it's possible to obtain Ramond backgrounds, more sectors of supergravity. We're also working on the topological twist for n=1 or n=2. Yeah, we are seeing that we get indeed the Chern-Simons theory and the B model itself as well. In this setting. So the point here is full BRST cohomology of n=2 or n=4 spinning particle, or n=4 we still haven't understood yet, gives the B model itself. Because it's already known that the B model can be a particle theory as well, but we want to argue that it's BRST of the spinning particle. So thanks a lot for attending and thanks for the questions.
Do we have any questions? Comments?
So do I understand correctly that you're working mainly in 4 dimensions, or does this go through also another?
I watched those in other dimensions, yes. So, well, eventually we were focusing on the equal. It's fun, it's more physical, right? But we do everything in other dimensions as well. There is no cancellation of any anomaly that tells us that we should work in D equal 4.
So the dimension view is arbitrary.
Yes.
Nothing weird happens if you go to dimension 42. Something like that.
No. No, there is nothing weird. It's because we don't have the conformal invariance of the string theory. That's
But even the supersymmetry, we will be all in 11 dimensions.
The supersymmetry doesn't know what she.
yes,
So-
exactly. So it's fixed to be
Right.
equal to.
We're covering the steering mouse
Yes.
at some point, so that is
So what would be the theory that you get
something else.
in way?
What's the question?
Right, so you did a superparticle, you saw at least the 4 dimensions that you get in the spectrum, you get superiors.
Yes. No, yeah means.
We get just
Yeah, just
ordinary.
like it.
Yes.
That's wonderful. So you say before you get gravity, not supergravity.
Gravity with a bish than the D.
Can you say more about what is the problem with the alpha algebra for the interacting?
So it's because of our mathematical knowledge. So you work so here this okay with the functions. Then when you also are equal 1 and also the other. These are actually just C, gamma, and beta. Okay. So for example, the ghost C for the unmissed comes with a beta anti-ghost of the worldline. You know that the mu2 for C, for example, with its C and C is and this is we will need something to pick some product that still lands in beta. So on the C, okay, we can still say okay, these are zero forms valued in the color group. However, with a beta, we cannot simply, we need something that multiplies them and gives us, instead of this square, beta square gives beta. And if you go on and you try to do this for everything, then you run into inconsistencies. So we need, there's some need of some product on the beta gamma C part that just does the right thing. We need to, yes. It would be nice to find some good product.